Stand on a street corner in Chongqing after sunset. The city is drenched in neon light. Autonomous cars glide past the pavement in absolute silence. On the sidewalk, a mechanical quadruped trots effortlessly beside a crowd of tourists. Cameras flash. People point and laugh. Looking at the sleek metal joints, the illusion is perfect. It feels like science fiction has finally arrived. It feels like the machines are ready to take over. Then the illusion breaks. Take that same multi-million-dollar robot out of the neon glow. Put it in an ordinary kitchen. Ask it to wipe a table. Ask it to fold a towel. It freezes. Its mechanical fingers twitch. It fails. It is a fascinating contradiction to watch. We've engineered the futuristic shells. We've mastered the silicon, the motors, and the battery packs. Yet beneath all that polished chrome, these machines are starving. They aren't starved for electricity or even ambition. They are starved for something far more ordinary. Physical data. They lack the recorded memory of simple human touch, the subtle torque of a wrist turning a doorknob, the friction of a broom sweeping a floor, the exact pressure of a hand gripping a glass. We built the bodies of the future, but they have no past. Now, out of desperation, a strange new industry is quietly taking shape. To feed these empty shells, tech companies aren't just coding in sterile labs. They're strapping wearable sensors onto everyday strangers. They're paying people to scrub their own messy kitchens just to harvest the footage. The path to the sci-fi future isn't being paved in high-tech research centers. It's being built in messy bedrooms through a bizarre, borderline dystopian scramble to digitize our most boring daily chores. Why is the most advanced hardware on Earth helpless without our dirtiest laundry? And what really happens when we finally teach these machines how to feel their way through our physical world?
It really just comes down to this fundamental mismatch in how we've trained artificial intelligence versus how physical reality actually works.
Right.
Like the large language models that run our digital world, the ones writing code and passing the bar exam, they are trained almost entirely on text.
Yeah, just massive troves of data from the internet.
Exactly. You feed a model 1 trillion tokens of text, and it learns all the probabilistic relationships between words. But physical intuition, it's just not a language.
No, definitely not.
You can't just write a textbook on the exact friction you need to hold a wet bar of soap without dropping it, and then expect a machine to read it and suddenly understand that physical sensation.
Yeah, because knowing the physics equations for friction isn't the same as actually having the sensory ability to manage it in real time. I mean, I think the average person looks at like one of those Boston Dynamics robots doing a backflip on YouTube and assumes, well, if a machine can launch itself into the air and land perfectly on 2 feet, it should definitely be able to wipe down my kitchen counter.
Right, because the backflip looks infinitely harder to us.
Really?
But that's actually the ultimate optical illusion of modern robotics, because a backflip, while mathematically complex, is entirely deterministic.
Deterministic meaning?
And it's a closed-loop environment. The engineers know the exact mass of every limb, the exact maximum torque of every single motor, and obviously, they know the gravitational constant of Earth.
Right. Gravity isn't changing on the mid-jump.
So when that robot jumps, it's just executing a highly optimized, pre-calculated trajectory. There are 0 surprises midair.
But a kitchen counter is full of surprises.
Utterly chaotic. Wiping a counter is stochastic. The sponge is squishy, and it changes density as it absorbs water.
Oh, yeah, I didn't even think about the water weight changing.
Or maybe the counter has a sticky spot of dried syrup, and that suddenly drastically alters the drag coefficient.
So the robot's arm hits that sticky spot, the resistance spikes unexpectedly, and suddenly all that pre-programmed mathematical trajectory is just totally useless.
It's useless. It doesn't know how to adapt. And adaptation requires a sensory feedback loop that current hardware simply doesn't have.
Let's talk about that hardware gap.
Yeah, let's just look at the mechanical reality of something boring, like picking up a pen from a desk. A state-of-the-art humanoid robot built for full-body tasks right now relies on roughly 50 precision actuators.
50 actuators. So those are the motors and gears acting as its joints.
Right, and 50 sounds impressive until you compare it to the human body. We operate with roughly 360 joints, controlled by over 600 muscles.
That's a massive difference.
So even before we talk about brain power or AI, the robot is operating inside this physical straitjacket. It's trying to replicate human fluidity with just a fraction of the mechanical articulation.
But the articulation isn't even the biggest problem. From the sources, it seemed like the sensory input was the real killer.
Oh, the bottleneck is the mechanoreceptors. When you reach for that pen, your eyes guide your hand. But the microsecond your skin makes contact with the plastic, your visual takes a backseat.
Right, you're not staring at your fingers while you write.
The nerves in your fingertips instantly gauge the friction, the temperature, the give of the material. If that pen starts to slip by even a fraction of a millimeter, your biological sensors detect that minute shift in pressure.
And it sends a signal up your arm.
Yes, up the median nerves to your motor cortex, and your hand subconsciously micro-adjusts its grip force in milliseconds. You aren't consciously calculating any of this.
You're just relying on decades of accumulated physical data, which is what we casually call muscle memory. Which brings to mind an analogy I was piecing together from the sources.
Right.
Tell me if this holds up.
Sure.
It feels like the AI industry has essentially created the world's most brilliant scholar who has lived their entire life locked inside a library. This scholar has read every single textbook on the biomechanics of swimming. They understand fluid dynamics perfectly. They know the exact drag coefficient of water, the precise angles the human arm should form during a freestyle stroke. They can mathematically model the perfect swim. But then you take this scholar, carry them out of the library, and throw them into the deep end of an actual pool.
They drown immediately.
They sink straight to the bottom.
Yeah, they sink because knowing the theory of water and actually possessing the physical intuition to coordinate your breath, manage buoyancy, push against the resistance, those are entirely different categories of intelligence.
And we've taken these brilliant LLM brains, bolted them inside titanium bodies, and thrown them into the chaotic, messy pool of the physical world.
And they are drowning. They have zero physical past to draw from.
So how do we fix it? Because tech companies are desperately trying to build a digital pool to save them.
Yes, the synthetic data engines. Because if they can't gather enough real-world data, since the robots are too clumsy to deploy into people's actual kitchens right now, the only alternative is to manufacture the data artificially.
They have to simulate the physical world.
This is the underlying logic behind systems like NVIDIA's Isaac Sim.
Right, Isaac Sim, which isn't just a video game environment. It's a hardcore physics emulator. But I want to push back on this a bit.
Okay.
If we can program a perfect physics engine where we define gravity, friction of wood versus carpet, how light bounces using ray tracing, why can't we just upload those physics directly into the robot's brain? Like, why do we have to run thousands of simulated robots through a digital obstacle course?
Because you can't explicitly program intuition. If you try to write rigid, rule-based code for walking, saying, lift leg to 45 degrees, apply X amount of force, lower leg, the moment the robot encounters a surface that isn't perfectly flat, the rules fail.
You trip some.
Right. Instead, you have to use reinforcement learning. In Isaac Sim, they drop a digital twin of a robot into a virtual environment and basically tell it, your goal is to walk across the room. Go.
And it has no idea how to do that initially.
None. It tries moving a motor, loses its balance, falls over.
Yeah.
The physics engine accurately calculates that fall.
So it learns from the failure.
Yes. The AI registers the failure, tweaks its internal neural network weights, and tries again, millions of times per second across thousands of simultaneous instances.
It learns to walk by repeatedly fighting simulated gravity.
It compresses millions of hours of trial and error into just a few overnight compute cycles. That's synthetic data.
But there's a limit to that, right? Because
Yes.
the simulation hits a brick wall at some point.
The physics engine is mathematically perfect, but reality is deeply inherently flawed. You can simulate a virtual rug with a specific friction coefficient. But can you simulate a rug where one corner is slightly frayed and the floorboard underneath is slightly warped and the humidity in the room has made the cotton fibers slightly swollen?
No, the computational load to simulate every single atom and its chaotic interactions would just be impossible.
Right. And this discrepancy between pristine math and messy reality is called the sim-to-real gap.
The sim-to-real gap.
An AI trained exclusively in a perfect simulation will instantly fail when deployed in the real world because the real world is full of unpredictable edge cases.
Right.
It lacks the data of clumsiness.
Which brings us to this incredibly visceral account in the research that completely changed how I view this whole data collection process.
Oh, the haptic suit guy.
Yeah. The synthetic data engines are producing perfect behavior, but the engineers realize they need the chaos of real flesh. The text in the source material paints this so perfectly. It says, Lin wore the haptic capture suit for the 11th hour today, his joints aching from the weight of the motion sensors.
11 hours in a heavy rig.
His job in the Shenzhen lab was no longer to demonstrate perfect posture. The synthetic data engines had already simulated 8 million flawless strides in the latent space overnight. What the algorithm lacked was the clumsy, chaotic unpredictability of real flesh.
Real flesh is messy.
Again, the lead researcher crackled through the intercom. Lin sighed, stepped forward, and intentionally caught his toe on the edge of a frayed rug, throwing his hands out in a desperate, awkward scramble to break his fall.
He's literally getting paid to trip.
On the monitor, a skeletal digital avatar mimicked his stumble, feeding the physics of human clumsiness into the neural network of the bipedal robot standing dormant in the corner. As the machine's optical sensors whirred, processing his indignity into its balance weights, Lin massaged his bruised knee. A bitter, absurd smile touched his lips. In this gleaming epicenter of artificial intelligence, his only remaining value was his ability to fail.
It is a profound realization. We spent the last decade trying to engineer machines that never fail, and now we are literally paying humans to demonstrate exactly how failure works.
I do want to clarify one term from that account, though. It mentioned the engines simulated 8 million flawless strides in the latent space.
The latent space.
What exactly does that mean here? How does a robot stride in a latent space?
Well, the latent space is essentially a mathematical concept. Imagine you take thousands of videos of people walking, and you ask an AI to compress all that visual and physical data into a highly abstract, multidimensional map.
Like a huge coordinate system.
Yeah. In this map, every possible variation of a walking stride is represented by a coordinate. A slow walk is in one area, a fast sprint is in another.
And the space between them.
The space between them contains all the smooth transitions, so when they simulate strides in the latent space, they aren't necessarily rendering a 3D video game character. They are mathematically traversing that map.
Just crunching the raw numbers.
Generating the raw numerical coordinates of perfect walking motions at lightning speed.
Okay, so the latent space holds the idealized mathematics of the movement. But Lin is out there physically bruising his knee because the math can't comprehend a frayed rug.
Excellent.
And this scramble for physical, clumsy data isn't just happening in specialized Shenzhen labs either. It's spilling out into everyday life.
Yeah, look at the company's shift in New York.
They are paying regular people to clean their own bedrooms while wearing cameras.
They are harvesting kinematic data from the most mundane environments imaginable. To teach a robotic arm how to manipulate a crumpled shirt, you need massive amounts of point-of-view data.
Showing how a human hand actually visually assesses the folds of the fabric.
The AI needs to see how the human decides where to grip and how much force to apply. You need the visual data of a human clearing a cluttered table, demonstrating the spatial reasoning of which object to move first.
We're seeing this bizarre, borderline dystopian scramble to just digitize our dirtiest laundry. But this reveals the core problem. If the bottleneck is physical data and simulations are trapped by that sim-to-real gap, then paying gig workers to scrub their kitchens on camera just seems hopelessly slow.
It's way too slow.
You can't scale a multi-trillion-dollar robotics industry by having humans manually act out every possible household chore. The math just doesn't work. So how do you bridge that gap at scale?
Well, you don't try to simulate it, and you don't try to act it out in a lab. You force the machines into the real world.
Ready or not?
You accept that the robots are flawed, clumsy, and imperfect, and you deploy them at massive scale anyway. Every failure out in the real world becomes a data point that trains the next generation.
But a free commercial market won't tolerate that. Right? A warehouse manager in Ohio isn't going to spend $1 million on a bipedal robot that drops half the boxes it picks up.
No, the free market demands a finished, polished product. They won't pay to be your beta tester for hardware.
Which means you need an entity with enough capital and leverage to absorb the cost of that failure in exchange for the long-term data harvest.
And according to the sources, no one is executing this strategy with more aggressive brute force scale than China. They're turning data collection from a laboratory exercise into a state-mandated industrial reality.
Let's break down the mechanics of this because the scale is just unprecedented. We're looking at a joint program launched by China's Ministry of Industry and Information Technology, the MIT, and the State-Owned Asset Supervision and Administration Commission, known as SASAC.
SASAC is key here.
This isn't just a suggestion or a white paper. It's a mandate. By the end of 2026, they demand the deployment of 10,000 humanoid robot units across over 100 high-value applications.
Which is an astronomical figure. We are used to seeing maybe a dozen experimental units wandering around a Silicon Valley R&D facility.
10,000 is wild.
Right. And by utilizing SASAC, the state is essentially using its own economy as a sandbox.
Because state-owned enterprises manage everything.
everything, from massive manufacturing plants to healthcare logistics and disaster relief operations. The government is ordering these enterprises to act as guaranteed customers.
They have to purchase and deploy these units on live factory floors, regardless of whether the robot is currently as efficient as a human worker.
And Xiao Hao, the robotics director at Vivo, provided the most accurate terminology for this shift. He noted that the industry is moving from demonstration-driven logic to task-oriented logic.
Demonstration-driven logic. That's the viral YouTube videos we were talking about.
For the last 5 years, humanoid robots were built for the demo. They were engineered to walk onto a stage, execute a flawless pre-programmed routine, pour a perfect cup of coffee for an executive, generate a viral video.
The engineering prioritized smooth, aesthetic movement in highly controlled environments.
But task-oriented logic means the aesthetic doesn't matter. The viral video doesn't matter. What matters is whether the robot can stand on an assembly line for 8 hours, deal with flickering overhead lights that confuse its optical sensors, manage the thermal wear on its joint actuators, and recover when a part comes down the conveyor belt slightly misaligned.
Just the ugly, gritty reality of actual labor.
Right. And when those 10,000 robots inevitably stumble or misjudge a grip or fail to navigate a cluttered warehouse aisle, all of that rich, chaotic, real-world failure data is instantly beamed back to the manufacturers.
So the state-owned enterprises are effectively subsidizing the world's largest physical data collection network.
That's exactly what's happening. They are forcing the sim-to-real gap to close through sheer volume of real-world deployment.
And they aren't just throwing hardware at the wall indiscriminately either. The deployment is deeply coordinated.
Very coordinated.
The research highlights the release of the country's first national standard system for humanoid robotics and embodied AI, which is abbreviated as HEIS. Over 120 different institutions and enterprises collaborated to write these standards.
Which is huge because standardization is often overlooked as just bureaucratic paperwork. But in hardware engineering, it is the ultimate catalyst for speed.
Because everyone is finally speaking the same language.
Right. If you have 140 different domestic manufacturers building 330 different robot models, which is actually what we saw emerging in that market, you risk total ecosystem fragmentation.
Right. If the robotic hand built by Company A uses a proprietary communication protocol that can't speak to the vision processing software built by Company B,
innovation just grinds to a halt. Every company has to build the entire tech stack from scratch.
So the HEIS standards break the technology down into 6 unified components.
6 components.
They standardize the basic commonality, the brain-like intelligent computing, the physical limbs and components, the complete machine systems, the application scenarios, and the safety and ethics protocols.
And what this actually means on the ground is plug-and-play modularity.
Like Lego bricks for robots.
An AI software startup can focus purely on the brain computing model, knowing exactly how to interface with standardized physical limbs that are manufactured by a completely different factory across the country. It lubricates the entire supply chain.
While we focus so heavily on the sci-fi appeal of these bipedal humanoids, we really have to look at the baseline of automation that already exists.
Oh, yeah, the current reality.
The 10,000 humanoid mandate is the bleeding edge, but the silent workhorses of this industrial reality are already entirely ubiquitous. The structural reality is that China currently holds roughly 51% of global annual industrial robot installations.
Over half of all industrial robots installed globally in a single year are going into Chinese facilities.
We are talking about an active fleet of roughly 1.75 million units on factory floors today. And these aren't humanoids. They don't look like us.
No, they are unglamorous, highly specialized pieces of machinery. They are 6-axis robotic arms. They're cobots, collaborative robots designed to work safely alongside humans that are welding chassis, painting components, and performing microscopic optical inspections on fast-moving assembly lines.
They don't need a generalized AI brain because their environment is perfectly controlled.
Right, they just do one thing flawlessly.
And it extends far beyond the sterile factory floor. The agricultural deployment in the sources is fascinating.
The DJI drones.
DJI is globally known for consumer camera drones, but they have deployed over 210,000 agricultural drones across the country. And these aren't just flying cameras monitoring crop health.
No, these are heavy-lift autonomous systems equipped with precise LiDAR arrays.
They navigate the incredibly dense, uneven canopies of lychee orchards in southern China. They calculate the exact trajectory required to spray fertilizer or pesticide without wasting a drop, and they are actively involved in the harvesting logistics.
And we really have to ask why this aggressive automation is the default strategy right now.
It's not just to show off.
No, it is not purely a desire for technological supremacy. It is a profound macroeconomic necessity. The working-age population is shrinking rapidly.
Right.
Furthermore, the demographic profile of the labor force has totally shifted. The younger generation has vastly different educational backgrounds and career aspirations than their parents.
They simply aren't willing to perform the monotonous, physically punishing labor of standing on a welding line for 12 hours or spraying pesticide in the humid heat of an orchard.
There's a massive labor vacuum.
But at the same time, the hardware costs have completely crashed. The research notes that the cost of a standard 6-axis robotic arm has plummeted by over 60% in a single decade.
A 60% drop is insane for hardware.
Because the localized supply chain is so incredibly dense and vertically integrated, these Chinese builds are rolling off the line at 30% to 50% cheaper than their Western equivalents.
So when a factory owner is facing a severe labor shortage and the robotic alternative is suddenly half the price it used to be, automation stops being a futuristic experiment.
It just becomes math. It becomes the only mathematically viable way to keep the doors open.
Which creates this massive compounding feedback loop. High demand leads to massive scale, which drives down the unit cost even further, which fuels even more demand.
It's a runaway train.
And this relentless industrial reality, this combination of state-mandated future deployment and absolute dominance in current generation automation, it has triggered a really fascinating cultural shift in the global tech ecosystem.
It has completely inverted the geographical center of gravity. For decades, the pilgrimage was unidirectional.
Always to Silicon Valley.
Right. If you were an ambitious engineer or a venture capitalist who wanted to see the bleeding edge of the future, you flew to California. You walked down Sand Hill Road. You toured the campuses in Palo Alto. But now, that compass has flipped, and it is driving an entirely new industry of tech tourism. There's a narrative in the sources that captures this exact psychological shift perfectly.
Mark's trip to Beijing.
Yes, I'm going to read this because it's so evocative. For 8 years in Palo Alto, Mark had sat in climate-controlled conference rooms arguing over LiDAR, supply chain bottlenecks, and safety red tape, convinced he was at the very center of the autonomous universe.
It's the center of the universe.
Now, standing on a bustling street corner in Beijing's Yizhuan district, the ambient noise of the city seemed to fade into a deafening silence. An unbroken line of driverless Tashes glided effortlessly through the evening rush, dodging delivery scooters and pedestrians with a fluid, terrifying grace.
Without safety drivers.
Beside him, a 23-year-old hardware lead named Chen casually tossed him a robotic hand actuator. It was lighter than Mark expected, beautifully machined, and cost a fifth of what his American team had budgeted for a clunky prototype back home.
A fifth of the cost.
Later, over plastic cups of beer and street skewers, listening to these young engineers casually discuss their weekly hardware iteration cycles, Mark felt a cold, sinking knot in his stomach. The technological hubris he'd carried across the Pacific evaporated, replaced by the quiet, crushing realization that he was no longer the architect of the future. He was just a tourist visiting it.
That narrative crystallizes the deep existential FOMO, the fear of missing out, that is currently permeating Western engineering circles.
The hubris evaporating.
Because it is one thing to read a white paper about autonomous vehicle deployment. It is an entirely different physiological experience to stand at a chaotic intersection in Yizhuang and watch a fleet of autonomous vehicles navigate aggressive human drivers and erratic scooters without safety drivers.
They're relying on that advanced vehicle-to-infrastructure communication, the V2X.
Yes, where the cars are literally talking to the traffic lights and the sensors embedded in the pavement. It's a living ecosystem.
So Mark realizes his team is arguing in conference rooms while the other side of the planet is actively iterating on the street. And this realization has spawned a booming market for what are essentially $9,000 deep dive tech tours.
Which is roughly 1.4 million yen.
We are seeing Silicon Valley founders, venture capitalists, and senior hardware engineers paying that much just to get a curated, multi-day look under the hood of these ecosystems.
They aren't flying to China to see the Great Wall anymore.
No, they are landing in Shanghai, Hangzhou, and Shenzhen.
They are touring BYD's manufacturing plants to understand how a company achieves such extreme vertical integration. I mean, BYD doesn't just build the car. They manufacture their own seats, their own battery cells, and their own proprietary semiconductor chips.
It's all in-house.
And they are visiting Unitary Robotics to witness the physical agility of humanoids firsthand. They are touring AI firms like DeepSeek to study how these teams are engineering highly efficient large language models at just a fraction of the compute costs that Western labs require.
But what are they actually learning on these tours? Like when Mark is sitting there drinking beer, listening to them talk about weekly hardware iteration cycles, how is that even physically possible?
It sounds impossible if you're used to the Western model.
Right, because I know software can be updated daily. You just push new code.
Yeah.
But hardware requires physical materials. You have to machine metal, pour plastics, build circuitry. How do you iterate hardware weekly?
You compress the geography of the supply chain until it operates like a single living organism.
The geography is the secret.
Take the Longgang Robotics Industrial Park in Shenzhen. In a typical Western hardware startup, the R&D team designs a CAD file for a new actuator casing. They email that file to a specialized mold maker 2 states over. The mold maker takes 2 weeks to machine the prototype and ships it back. The engineers find a flaw, tweak the design, and repeat the process. Every iteration takes a month.
But in Longgang, the geography eliminates the latency.
In Longgang, the R&D software engineers are sitting in an office on the 5th floor. When they finalize the CAD design, they literally walk downstairs to the 2nd floor where the mold makers are operating CNC machines.
They just walk downstairs.
The component suppliers are in the building next door, drawing from the massive electronics markets of Huaqiangbei. The assembly line is down the street.
Wow.
If they discover a flaw in a motor casing at 10:00 a.m., they can walk downstairs, machine a new mold by lunch, assemble the new prototype by 3:00 p.m., and run stress tests by dinner. They are treating physical metal and plastic with the same agile, rapid iteration methodology that Silicon Valley applies to software code. Concepts that take a Western team 3 months to push into mass production are scaling in Shenzhen in 3 weeks.
And the awareness of this speed isn't just restricted to elite venture capitalists anymore. The tourism demographic is expanding aggressively. The sources detail how general tourists are paying $92 for localized one-day tech tours. You can spend an afternoon riding in fully autonomous robotaxis, having your lunch delivered by a low-altitude drone, and interacting with specialized AI service robots.
But even more telling is the educational market. High school STEM students and their parents are booking these tours now. Think about the psychological impact on a 16-year-old engineering student. They aren't just learning robotics theory from a textbook. They are standing in the middle of the world's most aggressive, rapid prototyping hardware ecosystem, speaking with engineers who are only a few years older than them.
It completely recalibrates their understanding of global competitiveness, and it sets an entirely new benchmark for what next-generation education actually looks like. So we have this massive, sweeping macro reality. The factories are automated, the city streets are filled with autonomous cars, the humanoid robots are being forced into warehouses to close that sim-to-real gap. The macro level of embodied AI is scaling through sheer industrial brute force. But as the research shifts focus, it highlights a severe, seemingly insurmountable wall when we move from the macro to the micro. When we try to take this intelligence and put it on our own bodies, the era of AI wearables, we hit a profound physical limitation.
We hit the power wall.
The power wall.
The grand promise of the AI era is that intelligence will be ambient, right? You won't just type into a box on a screen. An AI agent will see what you see, hear what you hear, and assist you in real time.
Which requires wearable hardware.
Smart glasses, intelligent earpieces, biometric rings. But right now, the sophistication of the software has vastly outrun the physical capacity of the hardware to sustain it.
I mean, look at the most premium example on the market right now, Apple's Vision Pro. It is arguably the most advanced piece of consumer hardware ever engineered. It tracks your eyes with microscopic precision, it renders flawless spatial computing environments in real time, and it seamlessly blends the digital and physical worlds.
It's a marvel.
But to achieve that, the computing intensity is astronomical, which means the power draw is immense, which results in a battery life of roughly 2 to 3 hours. If the goal of an AI wearable is continuous, seamless integration into your daily life, having the device go dark before you even eat lunch renders the entire premise flawed.
And you cannot simply build a bigger battery because the human body has strict ergonomic tolerances.
It gets too heavy.
The bridge of the nose and the temples can only support a few dozen grams before the device becomes physically painful to wear. And high compute processors generate a tremendous amount of heat. If you push the processing power too hard, the device will literally burn the user's skin.
So the hardware engineers are trapped in this impossible vice between the insatiable power demands of the large language models and the unyielding biological limits of the human face.
Which perfectly contextualizes the exhaustion in the third narrative from our sources. We see an engineer trying to navigate this exact physical vice.
Yeah, I have that part right here. Let's dive into it. 3 grams. That was the chasm between a revolutionary AI wearable and an expensive paperweight that would burn a user's temple. In the cramped lab in Nanshan, Zhu squinted at the oscilloscope, his eyes bloodshot from 36 hours of chasing thermal leakage.
Thermal leakage is the enemy.
The breakthrough wasn't just the new magnetic battery capsule, a sleek, lightweight module designed to snap into the frame in milliseconds. It was the ruthless stripping of the onboard computing. He had finally forced the software to outsource its heavy cognitive lifting to the user's smartphone, pulsing only fragmented, low-latency audio and visual cues back to the glasses.
He had to dumb down the glasses.
As the power draw graph finally dipped, confirming an 8-hour continuous runtime without the hardware overheating, Yu felt no surge of triumph. There was only a profound, hollow exhaustion. He peeled the prototype frame from his face, tracing the red, tender indentation it had left across the bridge of his nose, and closed his eyes, wondering if they were engineering machines to fit the human body or slowly reshaping human flesh to accommodate the battery.
Wow. Zhu's hollow exhaustion is just the perfect embodiment of the current wearable industry. Because they cannot solve the fundamental chemistry of battery density fast enough, they are relying on architectural compromises. The magnetic battery capsules mentioned in the text are a primary example of this.
Like companies like Rocket and iFlyTech.
They've realized they can't put a heavy battery in the actual frame of their smart glasses, so they've designed these modular, lightweight battery capsules that look kind of like large supplement pills. When your glasses run low, you physically snap one of these magnetic capsules onto the arm of the glasses. It adds a few hours of runtime without completely destroying the form factor or causing ergonomic strain.
But the physical capsule is really only half the hack. Zhu's real breakthrough was the software compromise. The text notes he ruthlessly stripped the onboard computing. The sources refer to this architectural strategy as the cloud device split, or UCI. How exactly does this solve the thermal and power draw problems?
It solves the problem by making the wearable device intentionally dumb.
Dumb how?
Well, rendering AI-generated graphics and processing live video feeds requires heavy GPU and CPU usage, right? Which drains the battery and generates a massive amount of heat. So in the cloud device split, the glasses do almost zero actual thinking. The glasses serve purely as a camera to capture the world and a screen to display the result. The moment the camera captures an image, that data is instantly beamed via Bluetooth to the user's smartphone in their pocket or sent over 5G directly to a massive cloud server.
So the heavy cognitive lifting, the AI processing, happens entirely off-body.
The server computes the answer and beams a lightweight visual cue back to the glasses.
It's an elegant workaround, but it relies on perfect connectivity. Like if you walk into a subway tunnel and lose your 5G connection, your revolutionary AI glasses suddenly become useless pieces of plastic.
It's a stopgap.
The ultimate goal isn't to hack the architecture. The goal is to fundamentally alter the chemistry of power storage. And the research indicates that this leap in traditional power is actually arriving. Xiaomi has recently detailed their AI battery 2026, and the specifications read like a wish list from a sci-fi novel.
Yeah, the Xiaomi battery represents a total overhaul of the foundational chemistry. So traditional lithium-ion batteries rely on a liquid electrolyte to move ions between the anode and the cathode. But this liquid is flammable, it degrades over time, and if the battery is punctured or overheats, it can lead to a catastrophic thermal runaway.
It catches fire.
Xiaomi is moving to a layered solid-state electrode structure.
In a solid-state battery, they replace that volatile liquid with a solid conductive material. But how does an ion physically move through a solid?
That was the engineering bottleneck for decades. In a liquid, the ions essentially swim freely. But in a solid, the ions have to hop through the microscopic gaps in the atomic crystal lattice of the material.
Which sounds a lot harder.
It is vastly more difficult to achieve high conductivity. But by mastering this layered structure, Xiaomi has not only eliminated the fire risk, because there is no liquid to ignite, they have massively compressed the energy density.
And the numbers are wild. The sources claim an energy density of over 500 watt-hours per kilogram. To translate that out of engineering terms, that density could theoretically power a modern smartphone for up to 4 days of continuous heavy use on a single charge. And the thermal resilience is absurd. The solid-state design allows the battery to operate safely at temperatures up to 200 degrees Celsius. You could literally boil this battery in oil and it wouldn't explode. Furthermore, it can accept a full charge in roughly 10 minutes and survive 10,000 charge cycles, meaning the battery will long outlive the physical device it powers.
But the most fascinating element is how they actually manage that power. They call it the AI battery for a reason.
Right.
Traditional batteries use a basic rule-based chip called a battery management system, or BMS, to prevent overcharging. Xiaomi has integrated an actual large language model directly into the BMS.
Wait, they put an LLM inside the battery controller. Why does a battery need artificial intelligence?
Because energy demands in the AI era are not linear. When your device suddenly has to process a complex spatial environment, the power draw spikes aggressively.
Right.
The LM acts as a predictive intelligence. It constantly analyzes your personal usage patterns, the ambient temperature, and the specific software load. It anticipates power spikes before they happen and dynamically reroutes energy at the milliampere level across the battery cells to minimize thermal stress and maximize efficiency.
It is an intelligent, self-balancing energy ecosystem. So that is the bleeding edge of inorganic power. 4-day, fireproof, AI-managed, solid-state batteries. But the deep dive takes an incredible turn here, moving away from inorganic chemistry entirely.
Yeah, this part is wild.
If the ultimate goal is to power devices that are seamlessly integrated with the human body, why rely on mined lithium at all? Why not use the body itself? This brings us to the extreme frontier of bioelectronics, specifically the work of Professor Soo-Kyun Sean Choi.
Professor Choi's research represents a fundamental paradigm shift. We have spent the last century trying to make biology adapt to electronics. Choi is engineering electronics out of biology.
He is looking at ambient, physiological sources of power. His team has pioneered the development of paper-based microbial fuel cells.
Which is just... Wow.
I read this 3 times to make sure I understood it. A piece of paper and bacteria powering a device. Walk me through the actual biological mechanics of this. How do you extract an electron from a living cell and put it into a circuit?
It relies on a specific classification of microorganisms known as electrogenic bacteria. These are bacteria that, as part of their natural digestive metabolism, actually produce electrons.
In nature, they transfer these electrons to minerals in the soil.
So Choi's team engineers a specialized paper microfluidic matrix and embeds these dormant bacteria into it. When you introduce a fluid, whether that is a drop of wastewater in an environmental sensor or a drop of human sweat, the bacteria wake up.
They start eating.
They consume the nutrients in the fluid, and as they metabolize them, they excrete electrons. The conductive paper matrix acts as an anode, capturing those biological electrons and funneling them into a usable electrical current.
It is living circuitry. It is incredibly cheap to produce. It is entirely biodegradable, and it is perfect for single-use medical diagnostics. But he takes it further into the wearable space. The research outlines sweat-driven moist electric generators.
They have designed flexible, biocompatible patches that you just stick to your skin. The electrogenic bacteria embedded in the patch thrive on the specific metabolites found in human sweat, primarily lactic acid.
So as long as you're wearing the patch and naturally perspiring.
The bacteria continuously consume the lactic acid and generate a steady electrical current. It completely eliminates the need for toxic, rigid coin cell batteries in health monitoring wearables. Your biology literally becomes the battery.
And it gets even more radical. The bioelectronics move from on the body to inside the body. He has developed ingestible biobattery capsules.
This solves such a massive medical problem.
Right, because currently, if a doctor wants you to swallow a smart pill like a microscopic camera to image your digestive tract or an intelligent drug delivery system, that capsule has to contain a traditional battery. Swallowing a tiny lithium battery carries severe risks if the casing degrades in your stomach acid.
Choi's solution to this is just brilliant. His ingestible capsule uses bacterial endospores.
Endospore.
Yeah, these are dormant, heavily armored bacterial cells that can survive extreme environments. They remain completely inert as they pass through the highly acidic environment of the stomach.
But when they reach the small intestine,
when they reach the specific pH level and nutrient environment of the small intestine, the spores germinate. They wake up, interact with the intestinal fluids, and immediately begin metabolizing and generating electricity from inside your gut to power the medical device.
it is the ultimate synthesis of flesh and machine. And to wire all this together, he is engineering living liquid metal composites. They take flexible, highly conductive liquid metals like gallium alloys and merge them with these electrogenic spores.
The result is a stretchable, self-healing, living circuit board.
If the circuit tears, the biological components actually help bridge the gap. What we are witnessing is the dawn of the Internet of Disposable Things, where our micro devices are powered by the ambient moisture in the air, the lactic acid in our sweat, and the fluids in our own intestines.
If we extrapolate this trajectory, the physical constraints of power will eventually be solved, whether through Xiaomi's solid-state AI batteries or Choi's sweat-eating bacteria.
Which brings us to the final structural question of this whole new era. If we have the macro robots working the factories, and we have the micro wearables seamlessly powered on our bodies, how do we actually interface with all of this intelligence?
Right, the interface.
There has been a prevailing narrative in tech media for the last 3 years that AI wearables, the smart pins, the AI pendants, the augmented reality glasses, are designed to be smartphone killers. The assumption is that once we have ambient AI, we will throw our iPhones in the trash.
Yeah, that's the headline everywhere.
But our sources point to a very different consensus among the founders and developers who are actually building this architecture. Is the smartphone dead?
The overwhelming consensus is no. The smartphone is not dying. It is evolving into a server.
A server in your pocket.
The idea of killing the smartphone ignores how incredibly optimized the device already is. A modern smartphone possesses a beautiful high-resolution display for dense reading, a massive battery, exceptional thermal management for heavy computing, and ubiquitous cellular connectivity.
Trying to replicate all of that utility inside a tiny pair of glasses or a lapel pin is a fool's errand.
Who decided that carrying a powerful glass rectangle in our pockets was a problem that needed solving in the first place?
So the architecture of the future isn't about replacing the phone. It is about fragmenting the interface. The phone stays in your pocket as the heavy compute hub, the operating system, but the human body becomes the dispersed interface.
Right. When the AI needs to show you something, it projects it through the lightweight lenses on your face. When it needs to speak to you, it uses the discrete audio drivers in your ears. The experience surrounds you, but the phone does the heavy lifting.
And this architectural reality leads to a profound philosophical framework regarding where the actual commercial and practical value of AI resides. Dayuzen, a prominent venture capitalist in this space, articulated a concept we can call the harness theory.
The harness theory is brilliant.
He argues that we fundamentally misunderstand where the value of an AI model lies. The core intelligence, the large language model itself, is actually becoming commoditized.
Right. Whether you use an OpenAI model, a DeepSeek model, or a Meta model, they are all exceptionally smart.
The true value is created by the harness. Let's break down the mechanics of the harness. An LLM is essentially a brain in a jar. It can answer a complex question, it can write a poem, but cannot do anything. It has no hands.
The harness provides the hands.
The harness is the agentic software scaffolding wrapped around that brain. The harness provides the API connections that allow the brain to reach out and read your email, manipulate your calendar, authorize a payment, or send a motor command to a robotic arm. The harness transforms a passive chatbot into an active, autonomous agent.
And a perfectly designed harness frees up your cognitive bandwidth. You no longer execute the tedious micro steps of a digital task. You simply manage the AI agent that executes them for you.
And there's a massive data flywheel embedded in this theory, isn't there?
Oh, the company that designs the most intuitive harness captures the best interaction data from the user. That data is used to train an even more seamless harness, which attracts more users.
So the entities that control the agent architecture, the harnesses, are the ones who will extract the ultimate value from the AI revolution, regardless of who manufactures the physical glasses you wear or the solid-state battery in your pocket.
We are already seeing the power of the harness play out in open hardware ecosystems. The deep dive highlights a really fascinating example with Rocket's augmented reality glasses.
Rocket made a crucial decision. They built an open agent platform. They didn't try to wall off their software.
No, they allowed third-party developers to write their own harnesses for the glasses. And because of that open API architecture, an independent user literally hacked the ecosystem to create an agent that allowed them to control their Tesla using the glasses.
That is the defining insight. Rocket didn't have to spend millions in R&D to build a proprietary Tesla controller. They simply built a flexible platform, and the user's agent bridged the physical gap between the glasses and the car.
The physical hardware, the lenses, the plastic frames, the battery is just the delivery mechanism for the agent.
Which forces a total synthesis of everything we've explored today. The physical data bottleneck, the brute force factory deployments, the tech tourism, the bio-batteries, the agent harnesses. We have spent the last 4 decades living in a paradigm where engineers build a piece of physical hardware and then bolt a software operating system onto it as an afterthought.
We view the computer as the master and the software as the tool.
But the era of embodied AI reverses that polarity completely.
The hardware is inevitably going to commoditize. A 6-axis robotic arm will be as cheap and standard as a toaster. A transparent AR screen will be as ubiquitous as window glass. The true differentiator is the intelligence flowing through it.
The next generation of physical technology is not hardware with AI bolted on. It is an AI-first evolution, where the hardware exists solely as a physical vessel to carry out the intelligence's intentions in the real world.